So last time we looked at nuclear fusion and today we're going to be looking at fission. And this is the process that goes on in our nuclear reactors. The best place to start is probably what exactly goes on in our nuclear reactor. So let's look at that process. Well, it's something called a self or chain induced reaction. Now the key reactant or the key piece of fuel in this reaction is a uranium 235 nucleus. And this is almost the fuel that you use for fission reactions. Now, the first step in this nuclear fission process is that you have a slow moving neutron that joins with a uranium 235 nucleus. So when this neutron joins with a uranium 235 nucleus, it forms a uranium 236 nucleus, and this is unstable. So let's look at the equation to represent what happens here. You have a neutron plus a 235 uranium nucleus, and this will join together to form a 236 uranium nucleus. And because that nucleus is unstable, it will then go on to decay and form other nuclei. And usually it will try and form a barium nucleus and a krypton nucleus, but it may also form other elements. But the key thing that it also forms is 3 more neutrons. As we can see, this unstable uranium 236 will break down into smaller nuclei and extra neutrons. Now, the importance of these extra neutrons is that these neutrons will then go on to fuse with other uranium 235 and it will therefore cause more reactions. What will end up happening is these extra neutrons will join with the uranium 235 nuclei to form uranium 236, and this reaction will just keep on happening. And again, more neutrons will form, which will then join with more of this uranium 235 to form even more neutrons, and so on and so forth. Now, the reason why this is the reaction that we induce in a nuclear fission reactor is that the products here have actually got a slightly less mass than the reactants. And as we saw in the last video, this is known as a mass defect. And we know that because E equals mc squared, energy is released. Because some of the mass that was technically lost from the reactants has been converted into energy. Now, last time you were introduced to the idea of a binding energy, and that was the energy required to form a nucleus from its constituent nucleons. Now, there's actually another definition for binding energy, which is the energy required to break a nucleus into its constituent nucleons. Now, these two definitions are technically the same thing. Previously, we looked at the energy released when forming a nucleus. Now we're looking at the energy required to break a nucleus. Now, regardless of what definition you consider, the value of your binding energy, or the number, is same for both. And this is technically the definition that we look at when we're using or looking at fission reactions, and the other one is typically the one we look at when we're looking at fusion, because this definition of binding energy talks about breaking of a nucleus. However, in the exam, if it asks you for the definition of binding energy, it is perfectly fine to quote either unless it specifically asks for one of them. Now, I would recommend that you get comfortable with using both of these definitions. So if we look at our fission reaction again, we can say that the binding energy of the products is greater than the binding energy of the reactants. So what we can say is more energy is required in forming our products than that is required to break our reactants into its constituent nucleons. So let's look at binding energy in a bit more detail. Now here is a graph of binding energy per nucleon versus nucleus or nuclei with a different number of nucleons. So at the bottom you have hydrogen, which has one proton, then helium, which has two, and then it goes all the way up to iron, and then you've got these larger nuclei with like more and more nucleons. Now we know that for any reaction, the binding energy of your products must be greater than the binding energy of your reactants. Now, this is the only way that you can end up releasing energy. Otherwise, you'd need to put energy into the system in order for a reaction to take place. With this graph, you can see that, for example, the binding energy of hydrogen per nucleon is less than that of helium. So hydrogen can fuse together to form helium. And you can see that binding energy per nucleon of uranium is less than that of krypton and barium. So the uranium nucleus can break into a krypton nucleus and a barium nucleus. Now you can see that iron here is sitting at the top. It has the greatest binding energy per nucleon of any element, which means that iron is technically the most stable element. Now you can see that the binding energy of elements on either side of iron increase as you get towards it. Now this means that elements smaller than iron, these are elements that are on the left hand side of the graph or the left hand side of iron. These elements can fuse. Elements larger than iron can undergo fission. Now, very small nuclei like hydrogen and helium can therefore fuse together to get bigger and bigger until it reaches iron, and very, very big nuclei like uranium will undergo fission until it reduces size into smaller nuclei, but it can't go any smaller than iron. So iron is most stable and it cannot undergo fusion or fission. This is because it has the highest binding energy possible. So we started off by looking at the reaction that takes place in a nuclear fission reactor. So now let's look at the whole process of what goes on to produce the energy that we supply to our homes. And we know that energy is produced due to the mass defect. And as we can see here, there is some water flowing into this core. And in this core, we have our uranium fuel rods and our neutron. So with this water flowing into this core, we can say that heat is released. I'm going to show heat with these red arrows. And heat is released into this water. So this energy is used to heat water, therefore produces steam. Now, as you can see, this steam passes up these pipes and passes through a turbine. And this causes the turbine to spin. The turbine is connected to a coil in a motor. And if you remember from our magnetism, this will therefore cause a change in flux, therefore an EMF and a current will be supplied. And this is then connected to, let's say, a step up transformer, which will then carry this power across into our national grid. And that's actually how we supply most of the energy that comes to our homes. Now, you might be thinking, well, if you looked at our reaction at the beginning, we kept producing more and more neutrons. But what if we produced too many? And let's say we accidentally produced too much energy. So that's exactly why we need control methods. The first one is a control rod. What this does is it absorbs excess neutrons. So these control rods can be inserted into the chamber where we have our fuel rods and our neutrons, and it can absorb these neutrons in order to prevent further fission reactions from going on. Now, another thing that we have in our core is something called a moderator, and this can be something like a heavy version of water. And the reason we need this moderator, this water will surround our fuel rods and will be around our neutron. Because if you remember from the beginning, we said that we needed a slow moving neutron. And this moderator helps us. So this will slow down the reaction. And we need a slow moving neutron because otherwise the reactants will simply collide and not fuse. So instead of the neutron and the fuel rod joining together to form uranium-236, the neutron will just simply bounce off the fuel rods. So this is the reaction that goes on in a nuclear fission reactor, and this is what supplies most of the energy that we get in our homes.
Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.